Okay, we started with a short quiz that basically covers stuff that you would know from chapter one if you understand the toolkit functions and the transformations. So, we saw a graph about the right shape here and didn't give you a lot of time to work on these problems because this graph had the right shape, but it didn't have a scale. So just to review what you need to know about this function, it's one of your toolkit functions. You've got to really understand these toolkit functions, especially a few of them, okay? The quadratic, reciprocal, square, and cubing functions. And then the square root and the cube root. So you kind of want to review that maybe, but we need to move on here. So if I've got y equals x squared, I'm going to make a table. Now, your textbook tells you use a calculator to evaluate these things and so forth. And I'm not sure how much you're required in your section to be able to do the arithmetic. I'm going to mention the arithmetic. So x can be -2, -1, -1/2, 0, 1/2, 1, 2. And I think that the open math goes to -3 in some of these. Couple of properties that are real important, okay? -2 squared is 4. Because -2 times -2, two negatives gives you a positive. 2 times 2 is 4. -1 squared is 1. And you need to understand that not just by punching it into your calculator, but by writing out the arithmetic and make sure you know the rules. It's going to be very important because we're going to talk about power functions in a minute. And this is a power function. The cubing function is also a power function. We might review that real quick. Okay, -1/2 squared is what? Well, 1/2 times 1/2 is 1/4. A negative times a negative is positive, so we get 1/4. Make sure you understand fractions well enough to understand why that's 1/4. 0 squared is 0. 1/2 squared is 1/4. 1 squared is 1. And 2 squared is 4. This gives you a graph we can easily sketch. I'm going to put -2 here and 2 here. Well, actually, 2 ought to go a little further over because it's got to be the same distance from the y-axis as -2. Maybe that's a little better, okay? So this is an approximate graph. I advocate to be able to hand sketch these graphs, not just click on things and get the right answer in open math, okay? So you'll understand it better if you do. So anyhow, you have -1 here and 1 here. Halfway from -2 to 0 is 1. Halfway from 2 to 0 is 1. Halfway from -1 to 0 is -1/2. Halfway from 1 to 0 is 1/2. So what I've done is I've sketched an x-axis that's labeled with the x values -2, -1, -1/2, 0, 1/2, 1, 2. The y values, they go up as far as 4. So I'm just going to put y equals 4 up here. If x is -2, y is 4. So I've got the y equals 4 line above, ways above the x-axis. I'm not trying to keep equal scales on the x and y at this point. When x is -2, y is 4. So I draw the vertical line, x equals -2, and where it intersects the line y equals 4, I make a point. Then at -1, well, okay, y is 4 up here above the x-axis. Halfway between y equals 4 and the x-axis. Well, the x-axis is y equals 0. So halfway between y equals 4 and the x-axis is y equals 2. Halfway between there and the x-axis is y equals 1. Halfway between 1 and the x-axis is y equals 1/2. And then halfway between that and the x-axis is y equals 1/4. Hard to see those, but hopefully you understand. And what I've done in sketching this is I've drawn a line for y equals 2 that's halfway between y equals 0 and y equals 4, a horizontal line halfway between the y equals 4 line and the x-axis. The y equals 1 line is halfway between the y equals 2 line and the x-axis, which is x equals 0, and the y equals 1 line, and so forth. Okay, each of these lines is twice as close to the x-axis as the one before it, so that we've got a scale. Now, there are other ways you can do the scale. You don't have to do it the way I've done it, but I think this halving idea, cutting things in half, is real profitable for these power functions. Okay, so now at -1, we find that y is 1. So I draw a vertical line segment through what x equals -1. And where that meets the y equals 1, I draw a point. And then when x is 1/2, -1/2, y is 1/4. So I draw the line, vertical line, x equals -1/2. And where it meets the line, y equals 1/4, which is the lowest of the lines that I sketched, I draw a point. And then y equals 0, x equals 0. Then I do similarly. Not going to take the time to explain every point, but I do the same thing for the remaining points. I'm not going to label these vertical lines on the right-hand side of the axis, but it should be obvious from the way they were labeled on the left-hand side of the axis what they mean. Then we can sketch the curve. And this chalk isn't working worth a doggone. I have to whittle it down a little bit. Anyhow, you can see the curve. And now I've got a scale. Now, in your class, you might not need to draw all these horizontal and vertical lines, but you do need to label the x and the y axis. So the graph that you get might be labeled something like this. And the point -2, 4 is here. The point 1, 1 is here. The point 0, 0 is here. The point -1/2, 1/4 is like here. And, you know, your graph might end up something like this. Some dotted projection lines wouldn't hurt. But that's more like the way it's going to look in open math. Open math is not going to draw all these projection lines. Okay? Your instructor might not be drawing all these projection lines depending on how he or she wants to present the material. Okay? But that's what's going on. Now, the reason I present it that way is because if you've got y equals x cubed, well, I'm not going to, yeah, I am. Okay. I'm not going to do the, well, I'm going to do the negative values, Okay, negative 2 cubed is negative 8 because negative 2 times negative 2 is 4. Multiply that by negative 2, you get negative 8. Similarly, negative 1 cubed gives you negative 1. Negative 1/2 cubed, 1/2 times 1/2 is 1/4. Multiply that by 1/2, you get 1/8. And it's negative because you're multiplying negative 1/2 times negative 1/2 times negative 1/2. Three negatives makes a negative. And you get 0. And then you get 1/8 when x equals 2, 1 when x equals, 1/8 when x equals 1/2, x cubed is 1 when x equals 1, and 8 when x equals 8. Now, I want to look at just the part of the table. Well, look at enough of it. Between negative 1, x equals negative 1, and 1. And I'm going to look at the graph between negative 1 and 1 before I look at anything else. So here's negative 1, and here's 1. Up here, and I'm actually going to extend the y-axis a little bit because you want at least to have a sense that, no, I actually don't need to do that. Between negative 1 and 1, I just need a line for y equals 1. And I could label that by putting a 1 here on the y-axis. And then here's 1/2. Here's 1/4. And here's 1/8. Now what I've done is I've just drawn a y-axis. I've labeled y equals 1. And I've had an x-axis labeled negative 1 and 1 on opposite sides of the origin. And then I've got to do negative 1. You should see from the table that negative 1 cubed is negative 1. Or not, yeah. So I got to have y equals negative 1 on my table. So I'm going to label this point here on the y-axis negative 1. Then I can see that the point negative 1, negative 1 is right here in the third quadrant on the vertical line through x equals negative 1, on the horizontal line through y equals negative 1. At x equals negative 1/2, we have negative 1/8. Now, I haven't labeled negative 1/8, negative 1/4, negative 1/2, and so forth. We can see that negative 1/8 is going to be about here. So this dotted line, I've drawn a dotted line at y equals negative 1/8, 1/8 of a unit below the x-axis. And it's 8 times closer to the x-axis than negative 1. And 1/8 is 8 times closer to 0 than 1 is. And I label the point where x equals 1/2 on the right. I don't want to label the x equals 1/2 point on the left because my curve is going to go right through my label. But we understand that I've got to mark halfway between negative 1 and 0 on the x-axis. And I draw a vertical line there. And where that vertical line intersects the y equals negative 1/8 line, just a little ways below the x-axis, I put a mark. Then when x equals 0, y equals 0. When x equals 1/2, y equals 1/8. So I've got a point down here. And when x equals 1, y equals 1, I locate those points on the graph. Now I connect them with a smooth curve. That smooth curve comes up very steep, and then it comes through the x equals, well, through the point where x equals negative 1/2 and y is 1/8. So it gets up there, and it's got to start leveling off a whole lot. And then it actually levels off completely when it goes through the origin. And then it starts out very flat, but then goes up through the point 1/2, 1/8, and then through the point 1/1. And you get this shape that you should be familiar with. Okay? That's your cubing function. Comparing the squaring function to the cubing function, you see two things. The cubing function, since you're taking the third power, a third power of a negative number is negative, so the graph to the left of the y-axis is below the x-axis. To the right of the y-axis, it's above the x-axis. Okay, so there's the x squared power function and the x cubed power function. The thing you can see is that in both cases, when you hit the point 0, 0 at the origin, the graph flattens out. Okay, the graph here flattens out. Now, I have to say that Open Math has a problem where they do the cubing function and they draw it like this. I think somebody just is having a bad day because the people that write these problems, I think, know their math well enough to know better. Somebody really screwed it up. Okay, so from negative, well, they drew a graph that looks like this. And it goes through the x-axis. It's like a 45-degree angle. That can't happen. At 1/2, this thing is not 1/8. And it doesn't flatten out as it goes through the origin. And those are important properties for later. They're important properties for right now. So you got to understand that this graph has to flatten out. If you went to x equals 1/4, what's 1/4 cubed? It's 1/64. You would be 8 times closer to the x-axis than you are here at the 1/2 point. And if you go to x equals 1/8, you're going to have 1/256. Is that right? No, it's 1/512. No, wait a minute. 64 times 5, yeah, it's 512. Okay. At 1/8, it'd be 1/512. So close to the x-axis that you couldn't distinguish it. So the graph actually gets a little flatter than I made it here. But the important thing is it flattens out, and every power function flattens out at the origin. If you've got an odd power, the negative numbers give you negative values, and the graph is below the x-axis. If you've got an even power, you have an even number of negative signs for the negative numbers, and that gives you a positive result, and the graph is above the x-axis on both sides. Y equals x to the 4th, and I'm not going to put a scale on this. I'm just going to higher powers. Higher even powers look something like the squaring function, but they get much flatter, much quicker near the origin, and then they get much steeper. Okay, I'm going to make a note here. The graph that I've drawn here is not y equals x cubed. It's not a power function. So I'm going to kind of cross it out, indicate that don't take that graph seriously. Avoid doing this. Okay. The odd numbered power function, odd powers like x to the 5th and x to the 7th and x to the 9th have this basic state. And the higher the power, the more quickly they flatten out. So you see that this one flattens out a lot quicker than this one as you approach 0. Those are important properties. Okay, well, those are your power functions. Now, the power function I want to focus on right now is the squaring function. We want to talk about how the graphs of the squaring function change when you replace x by x minus 4, or when you replace x by x minus 4 and then double it, or replace x by x minus 4 and double it and then add 6. Well, those are your basic transformations. So I'm just going to draw a picture of the graph as you might see it. In open math, the graph of y equals x squared. No, I didn't draw that very well because I didn't actually plot points. And my positive 2 is a little closer to the y-axis than negative 2. So it's not a real good graph. It's a little lopsided, but it's still y equals x squared. We can label it that way. Y equals x minus 4 squared shifts the graph 4 units to the right. That's one of your rules of transformation. Horizontal shift. Make sure you have some understanding of that. So if 4 is out here, this whole graph gets shifted to the right. So that, let's say, this point at the origin, which I'll indicate by a red dot, moves over 4 units. Everything shifts 4 units. Every other point shifts 4 units. So x equals 2 kind of becomes x equals 6. X equals negative 2 kind of becomes x equals 2. And now we get a graph drawn pretty crudely. Looks like this. Let's put 6 a little further over because I don't have a real consistent scale here. So this graph, the x squared graph, shifts over 4 units. Every point shifts 4 units. The point 2, 4 here shifts over 4 units to the point 6, 4. Point negative 2, 4 shifts 4 units to the point 2, 4. So there's a picture of your graph. Now, if we double the values of x to do y equals 2 times the quantity x minus 4 squared, well, first we think of doubling the x values for the basic function so that every point moves twice as far from the x-axis. Well, the graph is going to look something like this. So that if I did this correctly, this arrow from the x-axis up to the y equals x squared graph, and it could be any point on the x-axis, is half as long as this arrow from the same point on the x-axis up to the vertically stretched function, because multiplying the graph by 2 vertically stretches it by a factor of 2. So that the graph of y equals 2x squared looks something like what I have here. Okay? It looks like the y equals x squared graph, but you've stretched it out in the vertical direction. So it looks a little skinnier, and every point is twice as high as the one on the x squared graph. It's important to understand. When we then shift this graph, okay, y equals 2 times the quantity x minus 4 squared is the 2x squared function, but we've replaced x by x minus 4, and that moves every point 4 units to the right. So that this graph of y equals 2x squared The vertex moves from the origin to the point 40, and the rest of the graph goes along with it. So here we have a graph of excuse me for 1 minute. Gotta pull out a deadly weapon here. Trim this chalk so that maybe it'll. Right, there's apparently a piece of granite or something in this chalk. Okay, so this graph of y equals x minus 4 squared, well, I'm labeling it now. Okay, again, that goes through the point 40, also the point 64 and the point 2. If you plug in x equals 6 or x equals 2, you're going to get y equals 4. Okay, and you can do that. The graph of the 2x squared function, 2 times the quantity x minus 4 squared, then the graph of y equals 2x squared shifts 4 units to the right if you replace x by x minus 4 to get 2 times the quantity x minus 4 squared. So the graph that I just drew is y equals 2 times x minus 4 squared. Okay, now I'm too high on the board to draw y equals 2 times x minus 4 squared plus 6. If the y equals 6 line is up here, then I'd have to raise the point at 40 up to the point 46. If x equals 4 and the function y equals 2 times the quantity x minus 4 squared plus 6, I plug in x equals 4, I get 6. So the graph of y equals 2 times the quantity x minus 4 squared plus 6 is going to be 6 units higher than the graph of y equals 2 times the quantity x minus 4 squared. We're adding 6 to all the y values. That's going to vertically shift the graph. Now that's a review of what you know from chapter 1. In chapter 2, I'm going to study quadratic functions a little more thoroughly. But what I've just drawn here is 3 quadratic function. Now, quadratic means you can take quadratic as meaning the y equals x squared graph with a horizontal shift, a vertical stretch, you do that first, and a horizontal shift and a vertical shift. Any graph that you can get that way. Okay, so let's take this y equals 2 times the quantity x minus 4 squared plus 6. Now, I've been talking for a while, but it's all review. So if you didn't understand everything I said, you probably want to spend some time reviewing chapter 1 so you have perspective on this and the transformations, and especially transformations of the squaring function. But I'm going to ask you if you could expand this. You know, x minus 4 squared. What's x minus 4 times x minus 4? And then what do you get if you do 2 times that and add 6? So I want you to simplify this down or expand it. It's actually simplified, we're expanding. I'll say y equals question mark times x squared plus the question mark times x plus a question mark. Now I'm going to erase those question marks and replace them with numbers, but see if you can figure out what numbers go here when you expand this expression. Now, of course, if you're watching this video as a distant student, you should be paused and working on this, okay? If you aren't, do it. Okay. Now, hopefully you've made your best attempt to expand this and hopefully you got it right. We'll see in a minute. But you might be hung up on x minus 4 times x minus 4. So let's just make a little note. What's x minus 4 times x minus 4? Well, x minus 4 times whatever is x times that whatever minus 4 times that whatever. So x minus 4 times x minus 4 is x times x minus 4 minus 4 times x minus 4. This is a distributive law. Now, I've written that badly, but it says distributive law. Okay. And if you're not really up on the distributive law, you really need to be. So that's something you have to review. It's not something I can take the time to teach in this course, but if you want reference to where we've talked about it in my intermediate algebra course, just email me or email me, because then I can give you a link, okay? Or just go to an AI or Google it, say distributive law. If you're in an AI, say, can you give me some examples? Okay? Can you give me an example to work? Things like that. Okay, anyhow, x then times the quantity x minus 4, we have to apply the distributive law again. That means x times x minus x times 4. Then minus 4 times x minus 4. Well, minus 4 times x is minus 4x. And minus 4 times minus 4 gives us this. So it's minus 4 times x and minus 4 times minus 4. X times x is x squared. X times 4, we'll write that as 4x. And we have another 4x is our third term. And then minus 4 times minus 4 is plus 16. The minus 4x and minus 4x go together to give us minus 8x. So that x minus 4 times x minus 4 is x squared minus 8x plus 16. Now I'm going to write that here. We have the x minus 4 times x minus 4 gives x squared minus 8x plus 16. And then we still have our plus 6. Well, what's 2 times the quantity x squared minus 8x plus 16? 2 times the quantity x squared minus 8x plus 16 is 2 times x squared. And 2 times negative 8x and 2 times 16. And then we still have the plus 6. So now we can replace the question marks. Y equals what times x squared? Well, it's 2 times x squared. What times x? Well, we have negative 2 times 8x. That's going to be negative 16x. 2 times 16 is 32, and add 6, we get 38. So the function that we get when we take the x squared function, shift it 4 units in the horizontal direction, positive 4 units. Well, first, we vertically stretch it by a factor of 2, like here, like I've shown. Then we shift that 4 units to the right. Then we raise it up 6 units, which I didn't have room to do because of the board being too high. Okay? Because of the graph being near the top of the board. This function y equals 2x squared minus 16x plus 38 gives us exactly the same graph. So let's see how we would analyze the graph if we were given the function in the form y equals 2x squared minus 16x plus 38. First of all, let's give this thing a name. Let's call this f of x. It's 2x squared minus 16x plus 38. And well, questions we ask. For what x value is y equals 0? Answer. Y equals 0 if and only if x equals negative b plus or minus the square root of b squared minus 4ac over 2a. F of x equals ax squared plus bx plus c. Now, what in the world do I mean by that? Well, let's go back to our function. Y equals f of x is 2x squared minus 16x plus 38. And the general form of this function is y equals f of x equals ax squared plus bx plus c. Now, if this function is the same as this function, what's the value of a have to be? Well, a is what's in front of x squared, so a has to be 2. B is what's in front of x. Now there's negative 16 in front of x. B equals negative 16. And C is the number that doesn't go with an x. That's 38. Now we want to plug these numbers into x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So I'm going to ask you, I'm going to pause for a minute, give you a chance to plug these numbers into this formula and see what you get. Evaluate what you get as best you can. Okay, so again, we're going to substitute a equals 2, b equals negative 16, c equals 38 into x equals negative b plus or minus the square root of b squared minus 4ac. all that, over 2a. So we get negative 16 plus or minus the square root of negative 16 squared minus 4 times 2 times 38. All that divided by 2 times 2. So that's just a pure substitution. We just replace these letters with numbers, negative 16 and 38. And nobody had any trouble writing that out. Now we have to do the arithmetic in this. We get negative 16 plus or minus the square root of negative 16 squared is 256. 4 times 2 is 8. And 8 times 40 is 320, but we've got to subtract 16 from that. And I think we get 304, is that right? Yeah. I think it's 304 over 4. Let me multiply it a different way. 8 times 30 is 240. And 8 times 8 is 64. 240 and 64 does give us 304. So just checking my arithmetic. Now it's going to turn out it doesn't matter too much. We have negative 16 plus or minus the square root of what? 256 minus 304 is 48. But it's negative. Again, check my arithmetic. If you plug, if you try to do the square root of negative 48, you find that it does not exist. This number does not exist, okay? Because you can't do the square root of a negative. So y equals 0 is not on your curve. Well, if we go back to what we saw from the transformations, you see that if we raise the graph of y equals 2 times the quantity x minus 4 squared, 6 units, the vertex, the low point of the 2 times the quantity x minus 4 squared graph is on the x-axis where y equals 0. And if we raise the whole graph up 6 units, that curve's not going to go through the x-axis. Okay? Now, if I had a negative 6 here, then that would pull the curve down below the x-axis and it would have to go through the x-axis at 2 points. Is that clear? So if we pull this thing down, lower it, then its vertex is below the x-axis, and it's a parabola opening upward. That means it has to go through the x-axis twice. Okay, so we've done all this work with the quadratic formula only to find out that y is never 0 for this function, okay? There's no x that you can plug in here that's going to make y 0. Do get some more information from the quadratic formula. I'm going to circle negative b over 2a. Now, my reasoning here is that negative b is halfway between negative b plus the square root and negative b minus the square root. And if my a, b, and c numbers are such that the number inside the square root turns out to be positive, that means that negative b is halfway between negative b plus that square root and negative b minus that square root. So that negative b plus or minus that square root divided by 2a is halfway between the two numbers that make this thing 0. And that's the x value that gives us the vertex, because halfway between the two zeros would be the vertex. So okay, this function has an axis of symmetry. It's x equals negative b over 2a. It's the part of the quadratic formula we get if we just ignore that square root. Just get rid of the square root, we get negative b over 2a. So whether you understand what I said before, that's formula for the axis of symmetry. Now, what do we mean by the axis of symmetry? Well, any parabola has a vertex and an axis of symmetry Talk's doing better, but still not great. Okay. Meaning that what's on the left of that axis of symmetry is just a reflection of what's on the right. Now, in chapter 1, you've encountered the whole idea of symmetry, but I'm not sure how much of it how much it's been emphasized, okay? But it gets emphasized a whole lot when you get into chapter 3, okay? So there's a picture of a quadratic function. Just in general, the axis of symmetry is a vertical line, x equals negative b over 2a. Now, what line is that for the function we're working on? What do you get if you do negative b over 2a? Go ahead and plug in the value of b and the value of a, and tell me what number you get. You can hold up fingers, or I can look over your shoulder. Okay, now, one thing. Okay, well, let's just do this now. For this f of x, the axis of symmetry is then negative b, well, b is negative 16. And it's actually negative b. So b is negative 16, but there's a negative in front of that. It's the negative of negative 16 over 2 times 2, which equals 16 over 4, which equals positive 4. Remember, b has a negative in front of it, so if b happens to be negative, you have the negative of a negative, okay? So anyhow, you get x equals 4, right? Okay, well, let's look back at the original graph we made for the function. Now, f of x is 2 times the quantity x minus 4 squared plus 6. We expanded that to get the function 2x squared minus 16x plus 38, okay? Which is a function we're just working on. But that function is exactly the same as this function. Now, where's the axis of symmetry for the y equals 2 times the quantity x minus 4 squared graph? Well, the axis of symmetry goes right through the vertex. That's the line x equals 4. Vertical line x equals 4. There's your axis of symmetry. Okay. Now, what did quadratic formula tell us? It tells us that the axis of symmetry is negative b over 2a. When we use the expanded form, it tells us that the axis of symmetry is x equals 4. Okay? Now, the graph that we're looking at is the graph of y equals 2 times the quantity x minus 4 squared. But if I raise or lower that graph, the axis of symmetry doesn't change. Okay? If I pull the graph down here, the vertex is still on the line x equals 4 if I pull it straight down. And if I raise it 6 units, as we'd have to do to get the function 2 times the quantity x minus 4 squared plus 6, the axis of symmetry is still going to be on the line x equals 4. From this, we can figure out where this graph is if we didn't already know it. Got to rearrange the boards here for a minute. What do I have behind that? All this. I want to keep that. So we'll do this. All right, now we've determined that the graph y equals f of x equals 2x squared minus 16x plus 38 has axis of symmetry x equals 4. So I can sketch a set of x and y axes, and I can draw the line x equals 4 to the right of the origin, to the right of the y-axis. I know that the vertex, the low point on the graph, has to lie somewhere on this line. That's all I know at the moment. Okay, so what I've written now, the vertex is on the line x equals 4. Y equals f of x equals 2x squared minus 16x plus 38. So if x equals 4, y equals f of 4, which is 2 times 4 squared minus 16 times 4 plus 38. Well, 4 squared is 16, 2 times that's 32. 16 times 4 is 64, so we have minus 64 and then plus 38. What's 32 plus 38 minus 64? Well, you can work that out. It's 6. So we know that our vertex is the point 4, 6. So we can draw a y equals 6 horizontal line if we wish. And when that intersects the x equals 4 line, we have the vertex of our graph. again, get our original transformations. Our transformations tell us, take the y equals x squared graph, take the y equals 2x squared graph by vertically stretching it by a factor of 2. Make the y equals 2 times the quantity x minus 4 squared graph by shifting that graph 4 units to the right. And then the y equals 2 times the quantity x minus 4 squared plus 6 graph by lifting that up 6 units. And if we do that, we find that the vertex goes up to the point where x equals 4 and y equals 6, exactly as we got using the quadratic formula, okay? Now that's a whole lot to digest, especially if, like most students, you're a little bit shaky on the whole idea of transformations. This whole thing might not be a big revelation. Bottom line is, if you have the equation of a quadratic function, a function in the form ax squared plus bx plus c, you can, number one, use the quadratic formula, which is always the same, plug in the numbers, and find out where the graph crosses the y-axis. And that, I'm sorry, crosses the x-axis where y equals 0, okay? Then, if you plug the numbers into what you get from the quadratic formula, if you throw away the square root, that's x equals negative b over 2a, you get the equation of the axis of symmetry, which in our example is a line x equals 4. Well, it looks like this. And if we plug x equals 4 into our function, we get y equals 6. And that's where the vertex is. And then our graph is going to go through that vertex. Now there's a little more detail, like you want to figure out where the y-intercept is and so forth. But you put all that together and you can graph any quadratic function. Okay? And that's a big deal. So if you can understand that, you've got a really good grasp on some good stuff. Okay? So I urge you to work on it. Pay as much attention as you can in chapter 3 and work out the details.